Okay, I am going to do a second example in section 5.2. Um, I think this is kind of an important example, and it's a variation of the example that they do in the book. Um, the example that you should look at very carefully in the book is, hang on, example 2. So this is based on example 2. It's on, I think it's on page 215 in your textbook, where they essentially solve the same equation, but they use different boundary conditions. They use y of 0 is equal to 0 and y of L is equal to 0. And they solve that equation. So notice that y of 0, 0 is the same condition, but now I'm using y prime of pi over 2 equals 0 as the other boundary condition here. Which again, you might think of as an initial condition because it's prime, but remember, we're solving, this is y as a function of x here, right? So it's x that's equal to pi over 2, not t. There's no t here. Okay, so this I'm going to solve this in very much a very similar way as example 2 on page 215. And I highly recommend you actually read that example first before attempting something like this. But it is done in a very similar way. So, okay, so the issue here is that we're solving the equation y double prime plus lambda of y equals 0. So this is a homogeneous equation, all right? Which means you notice that we always get the trivial solution. Y equals 0 is going to be a trivial solution. So that's one answer right away. But that's the boring answer, right? We want to find the non-trivial solutions. Okay, so lambda is just a constant, right? Lambda is just some number, right? That's the coefficient of y. It's just a constant. Right? Okay, so now the solutions we get really depend on whether this constant is positive, negative, or 0. So we actually have to divide this into 3 cases here, right? So the first case we're going to look at is when when lambda equals 0. Right? When lambda equals 0, 0 times y is 0. So you're just solving the equation y double prime equals 0. And you can probably do that in your sleep, right? You integrate once and you just get a constant. You integrate twice and you get a constant times x plus c2. And so what do you get when you plug in 0? You just get c2, which is 0. What do you get when you plug in L? Well, you get C1 times L plus C2, which is 0, equals 0. Well, we know L is not 0. L is the length of the beam, if you will. So we can divide by L, and we get C1 is 0. So if C1 and C2 are both 0, we get 0 plus 0 is 0. So, yep, when lambda is 0, with these boundary I'm sorry, not these boundary conditions, right? Oh, I forgot. We're doing these boundaries. So I'm doing example 2 again. So hang on. That's an easy fix. Okay. Okay, so C2 is 0, but now we need this boundary condition here, which has to do with y prime. Well, y prime, of course, is just C1. So it doesn't matter what number you plug in for x. There's no x. This is just C1, which is 0. So you get the same conclusion. C1 is 0, which means if C1 and C2 are 0, you only get the trivial solution. Y is identically equal to 0. Okay, so, and we already knew that that was going to be a solution anyway. All right, so now we have the second case, case 2. We're going to look at what happens when lambda is negative. When lambda is negative. And for convenience, we're gonna say that lambda is equal to negative alpha squared. So alpha is just some other number. In fact, it's a positive number. And, well, when you square it, it's positive, and then this negative just takes care of the fact that we know lambda is negative. Okay, so by making this substitution, the differential equation becomes y double prime minus negative alpha squared. So, oh, I'm sorry, yes, plus negative alpha squared, right? So that's going to be minus alpha squared. Oops, y double prime minus alpha squared y equals 0. And that gives us the auxiliary equation m squared minus alpha squared equals 0, which means that m is either plus or minus alpha. Right? And alpha is just some positive number. And so that should give you the solution for y. Remember, there's nothing imaginary here, so there's no sines or cosines. This is just c1 e to the alpha x plus c2 e to the negative alpha x. Okay? And we could leave the solution like that. The book seems to like writing it in this format. Remember, you can write it as, say, c1, a different c1, of course, hyperbolic cosine of x plus c2 hyperbolic sine of x. You don't have to, but I think in some problems it might make it easier. So we're gonna treat it this way, right? And so now we plug in the boundary conditions, right? The boundary condition, well, y of 0 is 0, right? That's the first boundary condition here. So when you plug in 0 for x, you just get c1 times hyperbolic c1 times hyperbolic cosine of 0, which is 1, plus c2 hyperbolic sine of 0, which is 0. So you just get c1, which is 0. So again, c1 is 0. Now, when you take the derivative, right, remember the derivative of cosh is sinh, so you don't get a minus sign here. This is just c1 sinh of x plus c2 cosh of x. Right? And now we're plugging in pi over 2. Now I know that seems weird here because this is not sine or cosine, but it still works. c1 times this hyperbolic sine of pi over 2 plus c2 times the hyperbolic cosine of pi over 2. We know that equals 0, right? Well, remember, c1 is 0, so we shouldn't have bothered here. That's 0. And then hyperbolic cosine of pi over 2, I don't know what that is. It's some number. So you can divide by that number, right? It's not 0. So you can divide by it and get c2 is 0. So if c1 and c2 are both 0, once again, that just gives you 0 plus 0. So this gives you the trivial solution, y of x equals 0. So far, pretty boring stuff, right? We don't seem to be getting anything other than the trivial solution, which, again, we knew that was going to work anyways. So whether lambda is either less than or equal to 0, you don't get anything interesting. You just get the trivial solution, the 0 solution. All right, but that brings us to case 3. And yep, this is going to be the interesting case where lambda is positive, right? I'm still going to do the same trick here. I'm going to declare lambda is the same thing as alpha squared. Now, positive, right? So since lambda is positive, we don't want the negative as we did in case 2, right? But that allows us to write the equation as y double prime plus alpha squared y equals 0. Now going to our auxiliary equation, we get m squared plus alpha squared equals 0. And so m is going to be plus or minus I alpha, right? So remember what that gives us. Instead of writing e to the I alpha x, we're going to use sines and cosines, right? So y of x here is just going to be c1 cosine alpha x plus c2 sine alpha x. Okay, so that's our general solution, right? Now to find the c1 and c2, we just apply the same boundary conditions, right? So Can I scroll down? Running out of space. Right. So remember our boundary conditions are y of 0 is 0, and then y prime of pi over 2 is also 0. So let's just plug in 0 into this. So we get c1 times the cosine of alpha 0. Cosine of 0 is 1 times 1, plus c2 times sine of 0 is 0. So we just get c1 equals 0. Right? See a pattern here. This seems to always be the case. Oops, c1 is 0. So effectively now our solution is just c2 times sine of alpha x. Okay. So how do we find c2? Well, we're going to plug in into the derivative. Oh, we should take the derivative, of course, y prime of x. Y prime of x is going to be, well, it's going to be c2 times the cosine of alpha x times alpha, right? Chain rule. So c2 alpha cosine of alpha x, right? Now we plug in pi over 2, and that gives us c2 times alpha times the cosine of alpha times pi over 2. So alpha pi over 2, and that's still equal to 0. Okay. Well, so what does that mean? So, right, we're assuming that c2 is not 0. Obviously, if it is, we get the trivial solution again. So we can divide by c2. And we're assuming that alpha is not 0 either, because remember, alpha is just the square root of lambda, and lambda is not 0. So neither alpha nor c2 are 0. So we can divide both sides by c2 alpha and get those out of the way. And now we're just solving cosine of alpha pi over 2 equals 0. And that's just a trig equation. Surely you remember cosine of theta is 0, means theta is just, well, pi over 2, or 3 pi over 2. So any odd multiple of pi over 2. What's the best way to write that? Pi over 2 times 1 plus, not n, but 2n. Right, because these are odd numbers, odd multiples of pi over 2. Yeah. Right, so it's basically just pi n plus pi over 2. Those are pi's. Yeah. Pi n plus pi over 2. Either way. All right, but now my theta is this, right? Theta is alpha, alpha pi over 2. Right, so that's equal to pi over 2 times 1 plus 2n. Well, you can divide both sides by the pi over 2. You can cancel these. And so that tells me that my alpha, right, these are just odd numbers, 1 plus 2n. Right, or 2n plus 1. Maybe I'll write it that way. Right, alpha is just 2n plus 1. Right, for any integer n, although, remember, I think we want alpha to be positive, so we're going to start this at n equals 0. Right, so we don't want any negative alphas, even though lambda would still be positive. We want alpha to be positive here. So, all right, so 2n plus 1, so these are just odd numbers, right? And of course lambda is going to be alpha squared. Right, so these are going to be the square of the odd numbers, 2n plus 1 squared. Again, for the same non-negative integers n. Okay. So notice that, right, these, you get a whole bunch of different values for lambda here as well as for alpha. It depends on n. Right, so actually we get a whole different, a lot of different solutions here. What do we get? So for our y of x, right? We get, notice C2, we never actually found C2. That's just an arbitrary constant, so we can leave it as C2 for now, times sine of alpha x. Now alpha is 2n plus 1, right? So 2n plus 1 times x. Okay, so notice that you get many different solutions with all various values of n here. Okay, again, starting at n equals 0. I think the book uses 2n minus 1 and it starts at n equals 1. It doesn't matter, same thing. Right, so these are the non-trivial solutions to the original equation, which I should remind you, the original equation was y double prime plus lambda y equals 0. So maybe I'll just copy that down here. So so this equation solves y double prime plus lambda y equals 0, and using the boundary conditions, y of 0 is 0 and y prime of pi over 2 is 0 as well. Okay, so another name for a problem like this, for an equation like this is called an eigenvalue problem. For those of you who've had linear algebra, you certainly remember eigenvalues, right? So that's what these lambdas are. Let me highlight these. These lambda n's, right? These are called eigenvalues, and so, right. So these are the eigenvalues of the problem. And notice that there's an infinite number of them. So when you took your linear algebra course, when you solve for the eigenvalues, depending on the dimensionality of the problem, right? If it was a square matrix, you typically only got 2 eigenvalues, right? If it's a 3 by 3 matrix, you got 3 eigenvalues, and so on. Well, here you get an eigenvalue for each n, and the n's just keep going forever, right? N could be, 28 million. So, because n is any non-negative integer, you have an infinite number of them. You're going to get an infinite number of eigenvalues. So you can think of this as sort of infinite dimensional linear algebra, right? And notice that the y-n's here, the y-n's, these are the eigen functions. You could call them eigenvectors if you're comfortable with the idea that functions are just sort of vectors in infinite dimensional space. Then you can call these eigenvectors, but the book, I think, appropriately calls them eigenfunctions. Right? So we have effectively solved this eigenvalue problem here. You could rewrite it as y double prime equals negative lambda y. Right? So you're thinking about the second derivative then as your linear operator, right, is equal to, right, lambda y. Although in this case it's negative lambda y, but that doesn't matter, right? So this should remind you, at least from linear algebra, right, ax equals lambda x is the eigenvalue problem, where A is a matrix in your linear algebra course. Here, A is really an operator, linear operator, which is really just the second derivative operator here, right? L is just d squared over dx squared. Yep, so yeah, slightly different than what you're used to in linear algebra, but it comes up again, and in fact this is, what makes this a little more abstract is the fact that this is sort of infinite dimensional linear algebra, and but this is effectively what happens. So in the original problem, when they say solve this differential equation with these boundary conditions, in the homework, you'll see that they say basically find the eigenvalues and eigenfunctions. And to do that, you go through these 3 cases. And typically 2 of the cases will be trivial, right? It doesn't have to be the less than 0, could be the greater than 0 that's trivial, or vice versa. But in this problem, only case 3 ended up with these non-trivial solutions, and you get sort of infinitely many, one for each n. So that's as far as I want to go in section 5.2. But there's probably a few more for homework, and I would at least, again, read example 2 at the very minimum on page 215. And it goes through a very similar argument here. giving you the eigenvalues and eigenfunctions for the same equation but different boundary conditions. So I hope that helps, and that should pretty much do it for section 5.2. I don't think I want to do anything more complicated than that. So that's in fact that's all we're doing in chapter 5.